All right. Hi, and welcome everyone to exercise course number 10, where we will codingly talk about exercise sheet number 10, which is about the stochastic gradient and also the stochastic gradient descent. And as usual, we start with a very quick warm-up exercise to get into the flow. And this exercise here is about the so-called implicit updates of the stochastic gradient descent. So the stochastic gradient descent, just to have a quick reminder what the stochastic gradient descent was. So it's tailored to deal with objective functions which have a sum structure of this kind. So it can write it down as the sum over individual fi functions, sum them up and then divide by n. And when n is large, this means that we have to compute n many gradients to get the gradient of f. So the idea of stochastic gradient descent is to get a stochastic gradient, as the name suggests, which is, of course, meaningful in the sense that it's a good proxy, a good surrogate for the gradient we are actually interested in. And one way to do this, the most simple way, is we sample one integer from 1 till n uniformly at random, and then we do we simply set as our gradient the gradient at that fi realization. This is the gradient we use for iteration. So this is the gradient used for the first order method. So it can be gradient descent. It can also be Adam, it can also be Nesterov accelerated gradient descent, etc. So the point is that you simply replace every time you need the gradient of f, you replace it with the gradient of the realization it. You sampled uniformly at random at the current location. And it turns out this is an unbiased estimate. So it's, from a statistical and stochastical point of view, quite a good idea. Or not a bad idea. Let's put it like this. And now what we will consider here, implicit updates, is, well, we have the usual way how to update the gradient descent at first sight on the right hand side, but with one difference, namely that we have here on the right hand side now the future position. So an implicit update in the sense that we have to solve at first sight here again perhaps non-linear problem, because the gradient of fi evaluated at theta t plus 1 doesn't need to be linear. So we have to solve here a non-linear optimization problem or non-linear equation. And what we can do is we can also write it as our good old proximal mapping we have dealt with on the previous exercise sheet. Namely, we can simply express the next update here at this position also as the proximal mapping of fit for lambda being equal 1, step size gamma t at the current position theta t. Well, how can we see this? Let's plug in the definition of the proximal mapping. For this parameter setting, it's the minimal theta which is closest to the theta t we plugged in here. Yeah, in the squared Euclidean distance sense. And then divided by 2 times gamma t. The gamma t is coming from here, this parameter. And then we add to this also the function we want to kind of minimize with the proximal mapping. So you remember proximal mapping is mapping the theta to the theta space, if it's outside, of course. So it's kind of also a projection, but it's a bit more than that because it's also projection and going into the direction where the minimizer of the function here in the argument is located. All right. Now let's define this thing here as p theta. Well, this is what you see here. So we are interested in the minimizer of this function p theta. Well, if we want to minimize it and we assume that the function f is convex, I guess I forgot to mention this here somewhere. So actually it should be also convex function. Because when we have a convex function, we can definitely find the minimizer, namely by looking at the point where the gradient of this function is 0. Well, what's the gradient of that function? The gradient of the squared Euclidean distance between theta and theta t by r. So we have now computed this at least 5 times or more in this lecture. So it's theta minus theta 2. The 2's are canceling out here and there. We are left with this plus gradient of fit at position theta t. We have to solve it with respect to theta, and voila, what do we get? We get this implicit update formula. So the minimizer of this function p theta is exactly this right-hand side we see here. So we can write it also like this. So the theta t plus 1, the value returned by the proximal mapping at the position theta t is having this structure, the same structure we have here. Okay, now quick warm-up as usual. Then still a rather warm-up exercise, but kind of interesting what the result is. Namely, we want to apply now stochastic gradient descent for this sum-structured objective function, where we have some data points z1 to zn, d-dimensional, and we are interested in minimizing the squared Euclidean distance from all these data points simultaneously, more or less. What's the minimizer of this function f? Well, we have here a convex objective function because all of these sum operations here are convex. So this is a convex function, and we know summing up convex functions gives us, again, a convex function. Also multiplying it with some positive scalar, which we do here, is also not changing the convexity. So we can again compute the gradient of this function, set it to 0, and solve with respect to theta to get the minimizer. What's the gradient of that thing? Well, so let's do this step by step. gradient of this thing, of a sum structured objective function, is gradients or sum of the gradients of each of the individual objective functions. Each of these here are, well, computing the gradient with respect to theta. Again, we should know this by heart now, is 2 theta minus z1, right? Because again, we have here, if we write this out, we have this structure here, right? And of this thing, we want to compute the gradient. And here we know it's 2 times theta. Here it's minus 2 times z. And this is a constant with respect to theta. All right. Good. Then, if we have it in this form, we can now solve with respect to theta. And what do we first see? The first component here inside the sum, 2 times theta, is independent of I. So we are summing up n times the same entry, 2 times theta, and then divided by 2 times n gives us theta. And the 2 can, of course, be written in front of the sum, so the 2 is canceling out anyways. So the remaining term is nothing else than the average over the zi's. Well, we have here a 0 on the left-hand side. We bring this thing here on the other side, and we get the objective function f is minimized, or at first its gradient is 0 only for the point where we average over all zi values. And because the objective function is convex, this is also once again specified here. But you can check this with the Hessian matrix, but you can also argue as I did before. So the Hessian matrix of this function f would be nothing else than, of the sum structured objective function would be the sum of the Hessian matrices of all these individual functions. And the Hessian matrix here is simply the identity matrix. How can we see this? Well, here we computed the gradient already, 2 times theta minus z1. And when we now consider, so we know from above, gradient of theta z1 is 2 times squared, is this thing here. And now again, doing another derivative round, let's put it like this. What we get is, well, gradient of the first projection in the first row with respect to the theta i's. Well, for theta 1, we get here a 2, then a 0, because in the first entry, the theta 2 is not available, and the same goes for the others. Computing the derivative, the partial derivative with respect to theta 1 for the second component of the gradient gives again a 0. For theta 2 in the second component of the gradient gives us a 2. There we get the 2, and then you see that essentially we get here the, I forgot the 2, right? 2 times identity matrix. And zeros else. Okay, so 2 times the identity matrix. So here again, the 2 can be written in front. It would cancel out with the 2 we have anyways here, so it's the identity matrix. The identity matrix is positive, semi-definite, all eigenvalues are 1, and so the objective function f is convex. So this thing here, the empirical average, is a minimizer of the function, which makes sense because the objective function is the squared Euclidean distance from all these points, and the point which is minimizing this distance is the Euclidean, the empirical mean of the data points. But now we have verified that this is the case. So it's common knowledge, but here we have now verified it explicitly that the empirical average is indeed some kind of the central point, and minimizing it with terms of Euclidean distance. All right, then just a quick check that we've understood what is going on, namely what are the components fi of this function f in the some structured way. Well, we kind of use this all the time with this violet color scheme. Namely, we considered here, when we computed the gradients, exactly these component functions fi. Also, when we computed here the Hessian matrix, we did this, and well, or yeah, okay, so almost, because we had the convention that f is of this form, fi theta, and here we have the 2 in front of that, right? So we have to, of course, include here the 1/2 as well, but well, this is simply a scalar multiplied to every of these things doesn't, but if we want to have it strictly in our form, which we had, we have it like this. Okay, the gradients, we almost derived it. We looked at this thing and derived the gradients. Now we have to divide also with the 2. We had a 2 in the enumerator before. We have now a 2 in the denominator as well. Both are canceling out, so we are left with theta minus the I for each of these I components. Okay, and then let's assume we run the stochastic gradient descent with the step size 1 over t plus 1 and start at the 0 vector. And now assume our random choice, the seed was such that every time we have sampled one of these component entries, that turned out to be cyclic. The chances are not high that you get this, but the chances are not 0. So it can happen that you get exactly this cyclic. So cyclic means in the first iteration you get for the component you will choose for the stochastic gradient 1, in the second iteration the second component, etc. And then from there on it goes on again. And now let's have a look at when will stochastic gradient descent, the plain stochastic gradient descent, without mini batches and such things, reach the minimum. So, quick reminder on the stochastic gradient descent, in each iteration, sample uniformly at random an integer between 1 and n, and for this sampled integer compute the gradient of the corresponding individual objective entry at your current location, and then use this as the representative for the gradient you have, and do the iteration step as before. Now what do we get? So for the first iteration, we start with the 0. For the next iteration, now we go from the 0 into the direction of the stochastic gradient, f1, theta 0. So for all fi's, it doesn't matter which theta we plug in, we always have that this is theta minus z1. Now this is what we just had here. This is what we definitely have. Okay, and using this every time, we simply have to plug in the corresponding zi. Yeah, so in the first round, it's the first z1, from which we subtract from the 0, from the current position every time, and remember, gamma t is 1 over t plus 1. Yeah. So in the first round, it's a 1. Okay, then quite obvious. What do we get? 0 minus z1 is z1. Next round, we go from theta 1, which is z1, into the direction of the stochastic gradient descent with step size 1/2. 1/2, because now we are one iteration further. We plug in our stochastic gradient, evaluated at the current position, which is z1, theta 1 is z1, and subtract from that the corresponding z component, which is z2. And now we see z1 minus 1/2 of the difference between z1 and z2. This is exactly the average between z1 and z2. Now, from z1, we subtract half of z1 minus z2 is in fact plus z2, which is divided by half, so we arrive at that. Now, next iteration, and we see where this is then going. Now, step size is 1/3. We start from the middle of z1 and z2. This is our current position, theta 2, and we subtract from that z3. And here, what we get is a short calculation. We have here z2 half. We can use here law of distributivity, 1 minus 1/3, and then plus z3 over 3. Yeah, this is what we get at this. This and this gives us, of course, this. And the rest is using law of distributivity. And 1 minus 1 over 3 is 2/3. 2/3 times 1/2 is 1/3. So this thing is again z1 plus z2 divided by 3. We can add the z3 here as well, and we get again nothing else than the middle between z1, z2, z3. Or the empirical average, let's put it like that rather. The empirical average of these 3 data points. And then you know where this is going to. So when you see at the structure, it will continue in fact. So we can also make it quite general for the general case. In the n-1 position, we will be at the point z or all zi's except the nth one divided by n minus 1. And this is exactly what we had before. We have that the step size would be 1 over n. Gamma n minus 1 would turn to 1 over n. And, well, as usual, we plug in the stochastic gradient at the current position. And then, once again, we only have to check that here we really get this result. So to see this, again, you have here minus 1 over n minus zn. This will give you plus zn over n. And now let's have a look at the rest. So at this thing here and at this thing here, we can once again use the law of distributivity. And what's the term we are subtract or multiplying out of it? It's the term that they have in common, namely the empirical average over the first n minus 1 data points. Here we have it multiplied with the 1, and here we have it multiplied with 1 over n, or minus 1 over n rather. This here is nothing else than n minus 1 over n, right? And so 1 can be represented as n over n, and then you see it obviously that this is n minus 1 over n. But then the n minus 1 and the n minus 1 here are cancelling out, so we are left with the sum over the first n minus 1 zi's divided by n. And then we add zn over n to it, so we have the sum over all zi's divided by n at the end, which is the empirical average over the first n many data points. So after exactly n many iterations, the stochastic gradient descent, well, if we have, of course, this lucky choice of the components, but actually you can show, this is only making the notation a bit easier when we have this cyclic structure. You can show if you would sample uniformly at random without replacement, the n many data points, you will end up exactly at that point as well. Simply because you have to, so you can relabel the data points and then consider here exactly the same routine. So sampling without replacement is actually only telling you the schedule of which component will occur. And when you here guarantee that every component of the FIs will occur at least once, you will end up with the empirical average at the end. But then something happens, of course, when we do another iteration, because the problem with the stochastic gradient descent, so unless we check at the current position whether the gradient is 0 or not, here it would be definitely a good idea to check whether the gradient is already 0, the full gradient. But then, of course, the question is, when do you want to do this check? Because full gradient computation is costly. But here it would actually pay off, because otherwise, when you do another iteration, you will go away from the minimum again. So you reach the minimum, the global minimum here, and with the next iteration, you will go away from that. So once again, doing the same arguments as before. How we have here this step size. Here's the stochastic gradients. We can once again write out this guy here as z1 over n plus 1. And here, and with this, we use again our law of distributivity and can conveniently express this as the sum over this zi's divided by 1 over n plus 1. So we have left the global minimizer with the next iteration. This is not coinciding with the empirical average anymore. It's something different, can also be very different from the global minimizer. If, for instance, the Z1 is quite large, an outlier point, perhaps, not very similar to the other ZIs, then this can be also be very different. So you see the difficulty with the stochastic gradient descent, when to stop, because you don't compute the full gradient in every time. You only have this one component entry, and only that one component entry is 0 doesn't tell you anything about the full gradient. The full gradient is perhaps not 0 at that point. So if you would run the stochastic gradient descent further, you will then return again to the global minimum. Exactly after n many iterations, after n many iterations, you will come back to the minimum again. Okay. We're good on time. So far, so good. Now let's have a look at the counterparts. We have the theoretical counterparts for the stochastic gradient descent when we are dealing with a not necessarily convex objective function, but which is smooth in the sense that, for the gradient descent, we have seen when we have a beta smooth function, not necessarily convex, we can still have at least one result which is at first sight okay, because it's telling us at least that we find some, or perhaps find a local minimum, or an extreme point within the iteration. In the sense that if we look at the minimum squared Euclidean norm of the gradients we encountered, then this minimum will tend to 0. And when it is 0, we know this is some critical point, and hopefully the global minimum, or at least the local minimum, which is okay, so which is not perhaps the best we can get, but good enough for our purposes. This is also sometimes fine. If you have, for instance, a function like this, then here would be the global optimum. So something like this. Here would be the global optimum with this function value, and the local minimum, which is also fine at this position, with this objective value. If the distance on the y-axis, so to speak, if this distance here is not that large, so it's only an epsilon, then the local minimum would be also fine for our purposes, perhaps. So we not necessarily need always to have the global minimum. Of course, it's the best we can get, but sometimes a local minimum is also quite fine. All right, good. Then let's have a look at whether we can show something similar for the stochastic gradient descent. And it turns out, following the lines of derivation we had for the gradient descent, we can do something similar for the stochastic gradient descent as well. And the first thing we want to show is this inequality here. Yeah. So at first sight, perhaps not quite obvious where this is coming from, but if you have looked into the exercise sheet number 7, you would have seen, well, this is nothing else than rewriting the beta smoothness condition where we use, instead of the gradient, the full gradient, the stochastic gradient. So recalling what we get from the beta smoothness of f, we get that f of theta prime for every theta prime is bounded from above by this quadratic function here, yeah? Where the quadratic, the leading higher order term is determined by this beta over 2 term here. And question is, of course, which thetas should we use? Which thetas and theta primes? And the thetas we want to use are the current iteration. Why would... Okay. Current iteration, and for the theta prime, I don't know where it's jumping up, we want to use this one. And well, then again, being quite colorful here, we get this one. Oh, here, theta t, theta, so on. And here we get this, right? Well, simple substitution. And from here, we have to think of, okay, where is the stochastic gradient descent coming into play? And it is coming into play when we look at the iteration procedure we have for the stochastic gradient descent. So how do we get to the next iteration from the current one? We use the stochastic gradient, the GT, yeah, which is the gradient of the component IT we have uniformly at random samples, evaluate at theta t. And if we plug in this iteration here, for the theta t plus 1 here, and subtract it, so what's the, or rather better, this here is equivalent to theta t plus 1 minus theta is minus gamma t gt, right? We bring theta t on the left-hand side, and then we get this on the right-hand side. So here and here we have this and this. And in Euclidean norm, we can forget about the minus, doesn't matter. Doesn't change the length. And then it's just playing around a bit. So minus gamma t times gt is the same as if we would multiply the inner product first with gamma t and then do the inner product. Here the gamma t in the Euclidean, squared Euclidean distance comes out of it as a squared term. And now checking what we want to have at the end. Checking at the end what we want to have. We see when we now bring this here on the left-hand side, bring this here on the right-hand side, we get exactly the claim, right? Gamma t times the inner product of the full gradient with the stochastic gradient is smaller than the difference between the values of the consecutive iterations plus this squared Euclidean term of the stochastic gradient. All right. From here, we want to proceed as follows. We want to show that we get here, so we can get here expected values on the right-hand side, actually. And here we simply have to use what we have shown in the lecture, namely that the stochastic gradient, this GT here, is an unbiased estimate of the full gradient. Yeah? So unbiased estimate means here expected value of GT conditioned on that we know that we are currently at iteration theta t is exactly the full gradient evaluated at theta t. So what can we say about the full expected value? Now, without the conditioning, we can use here the law of total expectation. Yeah, so law of total expectations. The expected value of x can also be expressed as a nested expected value where we condition here in the inner expected value on some random variable y. This is what we do here. Yeah? This is the law of total expectation. We have encountered this a couple of times in the lecture, and we use this here as well. And then, why do we use it here? Because this thing here is the full gradient when we condition on that. And now, when we are in the position that theta t is known, then this here is not a random variable, non-random. So it's a constant or a constant vector in this case. So expected value of a constant or a constant vector is the constant itself. All right, good. Then we have this inequality in A, what we just have shown. This is the A inequality, which we have inferred. Gamma step size times inner product of the full gradient with stochastic gradient is bounded from above by the difference of the function value of the consecutive iterations, and this gamma term, this squared Euclidean term of the stochastic gradient. Now, the monotonicity of the expected values. Monotonicity of the expected values. Just a quick reminder, it's telling us when we have two random variables, x and y, such that x is smaller than or equal y, then this already applies that expected value of x is smaller than expected value of y. Or put it differently, if you have an inequality, you can apply on both sides the expected value, and it still stays an inequality. And this is what we do here. So we have from A an inequality, we apply on both sides the expected value, and the inequality is preserved. Okay, and now we only have to rearrange things, see what is random, what is known, what can be computed. First of all, here, starting with this, gamma t is a constant. We can write it in front of the inner product of the expected value, doesn't matter. The same is here for the expected value of the inner product. So if we are in the case that theta t is known, this here is again something non-random, and computing the expected value of an inner product of something non-random, something random, is the same as if you would compute the inner product of this non-random thing and then apply it the expected value of the random thing inside that. Yeah, this is what we get here. So we can also write this in front of that. Similar things happen on the right-hand side, non-random. So first of all, we can, of course, we have here a sum structure. We can decompose it into the expected values of the individual things. The individual thing here, with the f theta t, this is non-random. So with the expected value, it stays f of theta t, which we have here as well. And the expected value of f theta t plus 1, this is something which we have no control over if we are in the case that theta t is known. So it stays random and we don't know the exact value. And for this last term, well, we keep it as it is, with the expected value around it. Let's go further. We know that the stochastic gradient is an unbiased estimate, and also that its expected value is equal to the full gradient if we are in the case theta t is known. So this thing and this thing here coincide. And what we get on the left-hand side is nothing else than the squared Euclidean norm of the full gradient times the step size. All right. And well, this is what we wanted to show. We have on the left-hand side gamma times step size times the squared Euclidean norm of the full gradient at the current iteration, and then here more or less the same right-hand side we had before, except for the two expected values we have now here and there. Okay, and from here, where are we going now? Well, we go to the following inequality. How do we get there? We simply sum up what we have shown in B. In B, we have shown that this here is smaller than or equal than this here. All right? And we sum it now up from 0 till t minus 1 for some fixed iteration number, capital T. And okay, this thing here, we can write it back actually at the f of theta t as the expected value of f theta t. And then, when we write this like this with the expected value outside, first looking at the difference and then computing their expected value. Now we could also just a quick, if we have it like this, we can also, thanks to the linearity of the expected value, right here, the sum inside the expected value. And if we write it inside, we get, we see here a telescopic sum. Namely, we get here f of theta 0 minus f of theta 1 plus f of theta 1 minus f of theta 2, and so on, till we arrive at f theta t minus 1 minus f of theta 2. Everything cancels out. this, and with the following one respectively. And what remains are only these two things here. Now the very first objective value we get and minus the very last. Okay. And then we can argue as quite similar to what we had before for the gradient descent. So the infimum of the objective value function is definitely smaller than what we have at the iteration t. So again, using monotonicity kind of, also with the monotonicity of the expected value, we can replace this with this and only make this larger or equal when we replace the objective value of f at theta t by the actual infimum. Okay, and now we realize we don't need the expected value at all. So this is in fact also an equality. By the way, this is not an, so less than or equal is not false, but let's be more precise, it's an equality. Why is it an equality? Because the infimum is deterministic, it's a fixed value. Your objective value is a deterministic function. So the infimum is somewhere, it's a real valued number somewhere. And unless, of course, we sample the first iteration somehow in a stochastic way, but let's assume for simplicity we don't do this, then this is also a fixed value. So we get here this one. And this is our claim we wanted to show. So the sum over the expected squared Euclidean norms of the gradients we encounter times the gamma t is smaller than or equal than the error we have in the beginning, objective value at the very first iteration and the infimum we want to have, plus then the expected values of the stochastic gradients with a gamma t squared multiplication. And now, from here, it's not that difficult to go to the next inequality. Namely, we assume, similar to the theoretical analysis we had in the lecture, that the expected stochastic gradient norms are bounded by some constant. So how can we use this? So we have our there's something missing, I see. So here, of course, when we take the minimum over the summands we had here, with respect to the expected value, then of course it should appear here. I need a bit more space. So this should be minimum of expected value f of theta t squared, and then the minimum here. And this is a big multiplication sign. Again, so from this inequality we have in C, we take the minimum in each summand here with respect to this expected value. So we can write it in front because it's one value, not depending on the t anymore. And this value can be expressed as the minimum here. All right. And then on the right-hand side, we simply use that this here is bounded by this, and we end up with such an equality. Now, we divide on both sides of the inequality with the sum over the step sizes we use. And when we do this, we see, okay, they are showing up exactly here, because, and this is our claim, because here the minimum is what we actually are interested in, and the remaining terms are exactly as they are claimed. Here, this is that one, and well, this is that one. Okay, now so we see this is easily inferred from what we have before. Okay, so now is the interesting part. What does this inequality telling us regarding a good choice for the step size? Yeah. So on the right-hand side, we have some trade-off regarding the step sizes. So the first term, which is reducing the influence, or which can reduce the influence of our starting error, plus kind of the fluctuation of the step sizes. How can we get rid of this trade-off? And we look at different choices of the step sizes, and see what happens. The first is we let it decrease in a linear manner. So the step sizes are gamma divided by t plus 1 for some fixed base value gamma. And in order to specify the O terms asymptotics, we have to recall a couple of things regarding the harmonic numbers or the harmonic series, which will occur. So first of all, the harmonic series up till iteration number t is lower bounded by the logarithm of t and upper bounded by logarithm t plus 1. So there's a quite nice way to show this via Riemann sum approximations, actually. But I don't want to go into details here because it's perhaps quite well known. If not, it's you can look it up. In this case, of course, so we had time to prepare this. What about the series where we are summing up squares of the t, 1 over t squares? Here, we only need an upper bound for that. And an upper bound for that is simply the limit value. If you would go with the iteration number t till infinity, then it's known. So if we are summing here up over infinity the t squares, then this value is exactly p squared over 6. This is you can write it like this, or you can also, of course, so you can also write it like this if you want. So if you have the infinity in the uppercase, then it's the convenience to mean exactly this here. So lim is t to infinity for this case. But anyways, the point is, if you would sum this up for infinity, yeah, you would get some finite value, namely p squared 6. And this is a increasing series, of course. Yeah, so you only add up here positive values. So if you forget about the rest until some t, you only make it smaller. So smaller the asymptotic value, which is p squared 6. All right, how can we use this now for our result we just had? So when we are in the case that the gamma t is of this form, then what do we get? Here in this denominator, we get here, yeah, gamma times the harmonic series actually. And when we now use a lower bound for the harmonic series, then we make this entire term only larger. So we can use this inequality to make one part of this inequality true. And let's write like this. On the other hand, we can also see, okay, so sorry, here is of course also 1 times the harmonic series, which we make only larger if we replace it with this. And now the other thing is the t squared series, which is essentially here, only with gamma squared, coming from here, the gamma squared. And this is bounded by p squared, pi squared, divided by 6, and here the 6 is already multiplied with the 2, giving us the 12. Okay, so
yt is not
pardon? Yt?
No, I was thinking like yt is a function of y, but you already considered that. Yeah.
You mean the gamma?
Yeah.
Okay.
The gamma, but that makes sense.
Yeah, so perhaps. So just to make sure, what we have is, in this case, gamma t, t0, t minus 1. This will be gamma over t plus 1, right?
When we square, we can move the gamma in front, that will be enough.
Yeah, and gamma t squared would be t0 gamma squared t plus 1 squared. So essentially this term here, only with the gamma squared. And the gamma squared is appearing here. And also because it's in the denominator appearing as a gamma itself, you only get the gamma here. Okay, and now what we see is this is an O of logarithm t. So it's converging quite slowly to 0. Here? Here?
Yeah.
What are we missing?
Like it's no only by log t, upper bound by log t plus 1.
Yeah, but we use it only in the denominator. So we make the term only larger if we use, so we have 1 over the term, and we make it only larger if we use 1 over its lower bound, so logarithm of t in this case. Now, with the +1, it would be not so nice, but hopefully, luckily we have this logarithm of t. But I mean, you see, when you have this 2 upper and lower bounds, that referring to the convergence behavior of this harmonic series as logarithm of the iteration number is okay. Yeah, so it's actually pretty close to that. All right, so we see first term is converging to 0 with the logarithmic rate, quite slow. And what about the second one? Also only logarithmically. So the total rate is only logarithmic. 1 O of 1 over logarithm t, if we have this step size choice here. What about another step size choice? Now let's try out that we only go as a square root of t plus 1 to 0 with the step size. Here, once again, we have to think of what is going on for gamma t. This is gamma square root t plus 1 with this choice, right? So this is how we choose it right now. So we have to think of what is going on for actually this series here. And this series is what we have here, which we can also rewrite with the index shift like this. Then again, you can trust me or also prove it via induction quite easily that you get a good upper and lower bound when you look at the square root of the number of iteration or summons you have here. For the lower bound, square root of the number of summons you have is a good lower bound, especially for small t's, and an upper bound, which is also quite good for smaller summons, but then comes a bit crude, is 2 times the square root of summons. So this implies that we have gamma times square root t is an upper bound for the sum over the step sizes, and we get an upper bound by 2 times gamma times t for the sum of the step sizes. When we do squaring, what can we say about that with this choice? With this choice, our series is t plus 1, right? Gamma t plus 1. And from above, we already analyzed what this will be. Namely, it will be lower bounded, but we only need the upper bound actually. So we know that this is lower bounded, upper bounded by gamma squared logarithm t plus 1. That's the harmonic series what we have here. This one here. Okay, and then plugging in everything. Oops. Plugging in everything, we have, on the one hand, the gamma p lower bound, which we can use here, and we can use here. We have the gamma t squared sum upper bound, which we can use for this thing here. And again, the gammas are such that you are left with the gamma in the enumerator with the simple gamma. And what we get here is a better rate, right? So this is now O of 1 over square root t. And here, yeah, it's a bit dampened by the logarithm in the enumerator, but still square root of t rate, which is not bad. But we know from gradient descent we get, so for gradient descent, of course, it's a t rate we get there and not the square root of t. So that is somewhat unfortunate. And finally, we can ask ourselves what happens if we choose a constant step size. A constant step size would mean that we are then, if we look at the sum over the gammas, we are summing up t times the same constant, namely the gamma. And similarly, when we look at the squared step sizes, we get here gamma squared summed up t times. So with this, we can see, well, the sum over the gamma t step sizes is gamma t times t. Here we get a gamma squared times t. Here we get a gamma times t. The t's are canceling out, and we are left with the gamma here. Okay, so what we see here is one term which is going to 0 quickly, actually, so with a rate of t. And here we have a constant term, So constant term which we could make smaller if we choose a smaller gamma. But then, of course, when we choose a smaller gamma, the first term will be higher, where the gamma is in the denominator. But if we want an error, so this is coming back to what I was referring to at the beginning, if we are actually only interested in something which is good enough, perhaps not the optimum one, but you want something which is good enough, then you could say, all right, regarding this result here, I simply set the gamma smaller than the result I want to have, the epsilon I want to have. And then you see, okay, here something, of course you have to rescale it a bit with the terms which are appearing here, the beta and the v squared, and play around with that. But you could get here something which is then smaller than the epsilon you want to have for these two terms. Also, this result here is kind of showing also why these epoch strategies we talked about in the lecture are not a bad idea, that you always make this, you use a constant step size and then make it smaller after an epoch, because you fix the epoch, the number of iterations in your epoch, you fix the step size for that epoch, you profit from this fast convergence of the first term, where you kind of reduce the error you do in the beginning, and then, well, you have this constant term. Then you run a new epoch with a better, hopefully better starting position with a smaller step size gamma. So the additional constant you have here with the gamma will be smaller. The error, the beginning error is smaller because you learned something in the epoch before. And again, you make here the convergence quicker. Again, next epoch, you start with, again, a better starting position and smaller gamma value and so on. Everything then is going to zero with this epoch-wise strategy. And so this is perhaps also showing you why these strategies are in fact quite useful from a theoretical point of view.
Like the way I know it, they do an update of the match on subset only, and then the step size is also after all.
Well, this is then how you specify the epoch, right? As a mini batch size.
Okay.
Yeah.
Okay, so what doesn't necessarily it has processed the whole data.
I mean, you are quite free how you specify the epoch. So one common way is use the simple gradient descent with a mini batch size 1, and then do these iterations after a fixed number of times. You update the step size. You can also specify an epoch of one mini batch, after running one mini batch and then adapting the step size. There are kinds of strategies. Some are really good in this scenario, some are better in that scenario, but this quite common technique with the epoch, as we have explained it in the lecture, this is the one, which is overall always doing a good job, I would say. All right, so we have 10 minutes left for the exercise, the practical exercise. But I think this is fine because I won't go too much into the details. Clear. Because what we want to do is simply compare the stochastic variance of gradient descent and the Nesterov accelerated gradient descent with their full gradient counterparts in our usual setting. And after loading a couple of things, and also things we already know. So the new function we have here is the gradient with respect to one component, fi, which is given here, for which I actually also have a mini batch variation I see here, but we don't use this at all, I guess. But you could, so here mini batch, you could specify the indices of the mini batch, and then you will have the stochastic gradients based on a specific mini batch as well. Okay, so this is a verification. If you use as your mini batch all possible entries, you should, of course, then have the full gradient, and this is what you see here, right? So the mini batch computed gradient using all possible entries is corresponding to the full gradient. Okay, then gradient descent as we had it before, the accelerated gradient descent extension, where we have then the momentum term involved, and then we go to the stochastic variance, where we simply extend our gradient descent functions with the components or one Boolean stochastic, which is by default false. Also mini batch size is here included with mini batch size 1. And the big difference is if the stochastic Boolean is true, we compute, of course, then we use the stochastic gradient computation where we sample uniformly at random integers, how many, mini batch size many, and then use these as the gradients for our gradient update in the accelerated or in the ordinary. Okay, and then we can run our algorithms. So the gradient descent as before. We can plot it again. When we do the gradient descent, we go quite quickly to the minimum. We can run again also the accelerated gradient descent. See what is going on there. Again, we are going quite quickly to that. What about the stochastic gradient descent? Yeah, with a mini batch size of 1. So by default, it's mini batch size of 1. With the same naive choice here. Yeah, so some values. Let's have a picture. What is going on? Oh, we see it's first going away, and then at one point it's doing a very good step, getting closer, but then it might happen that it's kind of going around this minimum and not stopping at some point, but rather fluctuating around some objective values which are close to optimal but perhaps not optimal. What about when we do the stochastic version of the accelerated gradient descent? Here something similar happens. Oh, this was fast. So here you're jumping over it, going even one step further because of the momentum, of course. We still have momentum, but then we go back and are somewhere there in the neighborhood doing some steps around that. Yeah, so you see also these objective values are kind of in the same range. Here and there are some outliers, so 50 here, but then we go back again to something closer to the minimum objective value. Then we can also run all of these for the Lipschitz continuous case and have a look at what is then going on for the stochastic gradient descent. Yeah, quite interesting what is happening here. So you're jumping away with the very first one and then correcting yourself over the time. Yeah, this is now going the steps back. Here we can have a look at the accelerated stochastic variant again. I'm not going straightforward to this minimum, but jumping around. Accelerated, without stochastic components, goes directly to the minimum point. Then we can also compare it with the choices when we know that we have a gamma well conditioned function, which we have. And then finally also plot all these objective values into one plot and see the behavior over the number of steps. And it's, of course, no surprise. The non-stochastic variants, which are using the full gradient, they are going very quickly to the minimum, and all these dashed and dotted lines. So the dashed lines are I forgot the stochastic gradient descent. I only plotted the stochastic accelerated gradient descent. These are the dotted lines. So the dotted lines, you see, they are going down at the beginning, except for the smoothness choice. In the smoothness choice, we are doing something not so good, but then we do from time to time a good step, but then here after iteration, I don't know, 27, we are doing something very bad. We were going away from that. And this is something you sometimes see when you choose the wrong step size. So here we have gamma well conditioned. Gamma well conditioned is the best choice if we would use the full gradient, but this is perhaps not the best idea when we use stochastic gradients. So there it should be rather that we make the step size a bit smaller. So you remember the
normal solvents. Like on n, we take our image size, and so we multiply by image size by
the step size, you mean?
Yeah, the gamma well condition.
I mean, we could try it out. So choosing the step size, this is art, I would say. This is for this. Yeah. And also here. It's one, pretty much. But I thought I haven't specified it. It's 6, 8, 0. Yep. Oh no, this was not the problem actually. So it did not even come to that. Or did it?
I just read something French.
Let's specify it rather here. Gamma well conditioned trial, where we have it like yeah. Exactly.
See if you have access to X or pessimistic rather than.
Yeah, it's just overly specified. It's a global parameter. Okay, but then let's see. Yeah, so not doing anything. So it's stuck. Yeah, so this step size was too low. But if you would, I don't know, take here something like beta. I think 4 or 3 would do the job, perhaps. I get something better. As I said, it's a bit hard to tune the step size, especially a constant one. This is why you have all these kind of heuristics, yeah. So where you have this rule of thumbs, which are quite useful in practice, and yeah. So the theoretical ones. So what you can observe is reducing the step size over the time is a good idea and something you should do definitely. But don't reduce it too quickly. Yeah? So at the beginning, a larger step size is fine. And then going down, yeah, in a moderate way, let's put it like that, is fine. Yeah. But starting with a too low step size and then also decreasing it then, very bad idea. We can also have a quite drastic observation here, I guess. This was in this more where we have larger data. I think here it exploded at some point. Yeah, exactly here. With the stochastic gradient descent, yeah, it's even. And this is SAGDs. Other 3 ones. This is. Yeah, so stochastic accelerated gradient descent is doing this funny thing, because what we used here was again the wrong choice for the gammas here, in the sense that 0.05 as the base rate is in this case a bad idea, although the beta, now the beta, or rather the 1 over beta would be 0.43. If we would reduce it even further, this base rate, then yeah, it's getting better, but not that much better. Here, as you see, it's kind of hard to tune it. If we make it larger again, yeah, so that we have larger steps at the beginning and then moderately smaller ones, yeah, you see what is going on in the beginning. You are completely off. Yeah, you're completely off, and then getting better over time. But I mean, okay, worse than that cannot be. So you see the choice of the step size is not always so obvious. Also, okay, we run it only for 50 steps. I mean, you have to run it a bit longer than that, actually. But then the plots are kind of uninteresting because we don't see this. I mean, we would see still the gap between the full gradient versions and the stochastic ones. But yeah. So in the end, it will converge. Yeah, it will take time, but it will converge. maybe when we use a larger number of iterations. Oh, did I? Why did it not? Oh, I'm. Yeah. Okay, I get it. This is only for the gamma well-conditioned case. Of course, we have to change it also for the others. And then we run everything again. And then, well, you see the smoothness choice is going down slowly. The constant step size is doing actually quite good, right? So this is interesting. And for the Lipschitz choice, this is where we have the square root. Yeah. Yeah, so Lipschitz choice with the square root of t. Perhaps if we here also make it a bit larger. That's doing better because the constant step size is now. Oh, no, the red, yeah. Now it was a bad idea to make it.
Because it's stochastic, so it needs to be more samples until it actually reaches consensus.
Yeah, but we can also, which we haven't done yet, is also look at the influence of the mini batch size. So let's perhaps, I don't know, 10. Is this the right one? No. It's not the right one. Let's have a look what we get then. I had here already this idea, but did not. So this is working, right? Perhaps something I should. Yeah, so there was no error message, so this should work. And now with the mini batch sizes, yeah, you get a so mini batch size of 10. The picture is different, right? So you have a smoother behavior going down. Of course, from now and then it can also go up, but it's now having a stricter decreasing behavior, yeah, which you would expect, because with a larger mini batch size, you are stabilizing the entire procedure. And of course, the higher we choose the step size, the mini batch step size, yeah, the more we resemble the full gradient, of course. We could, but I haven't implemented it in the right way for doing this, because you remember from the implementations, I always use this also to track the objective value. We have to more or less do the difficult computation, namely the the matrix vector multiplication needed here. If we would, so if we would exclude this line here, where we compute this objective value, then, I mean, we could, of course. Okay, we are a bit over the time, but well. Oh no, I have a meeting at 6. But quickly we can check it. Perhaps, yeah, so it's here not so. Okay, so when we exclude it, then the time for full gradient 0.64. Also for accelerated gradients, 0.06. Okay, I guess there's something. Well, of course. This was not enough to just uncomment this. We would have to look into this compute gradient methods where this x theta I computation is. As I said, with this computation, it's difficult to really look at the difference regarding the computational time because we track here every time also the objective value. So of course, this would be also an interesting point to investigate. But as I said, I have to jump. So thanks for the attention. And then next time we talk about the mock exam. All right. Bye-bye.